So in the last video, we actually solved for the matrix K, which is also known as the Kalman gain. And if you go back to the last video, you remember that our Kalman matrix K, our Kalman gain K, which is a matrix, we said that this was equal to P bar times C transpose times S inverse. And we got to this formula using the methods that I described in the last video. If you're not familiar with this, please go back and watch it as I explain the derivation of it. But in this video, I'd like to now use our new knowledge of how we got K and what K is equal to pretty much make sense of the rest of the equations in the Kalman filter algorithm. So we saw that our update step, our update on x hat of t was equal to our estimation of t, which we set as x bar of t, plus some Kalman gain k times the actual thing that we're picking up from the sensor, whatever we're measuring, minus our estimation, which is given by z bar of t. This was our update step for x of t, which we denoted x hat of t. And now we actually have that Kalman gain k right over here. We actually have that value solved now. So first we need to figure out the Kalman gain k. We plug this in with our equations, and then we can perform the update on x. But there's also an update that we have to do for p, right? The covariance matrix p, because what are we doing really? Again, we're stating the goal of the Kalman filter, minimize the trace of the matrix p, right? So the only way we can do that is if we actually make updates based on our new information. So what we saw is that x hat of t was this, but there's also an update for p hat of t. And it's not so clear how we get to it, but let's say we multiply this matrix K times K transpose S, right? So we have K transpose S times K, right? And this is going to be equal to P bar C transpose S inverse times K transpose S. All right, so let's go ahead and solve this. We get here basically K S K transpose. I'm supposed to write this on the other side, but either way, K S K transpose was equal to P bar C transpose K transpose, and S times S inverse actually gives us back the identity matrix. So this is essentially the same as multiplying by 1 in an algebraic expression, but here we're saying that it's the identity matrix. And this is a very common fact in linear algebra, that the inverse of a matrix times the non-inverted matrix is equal to the identity. And we already saw that the identity matrix times this will just give us back this. So we actually don't have to write the multiplied by the identity matrix. It's similar to how in algebra we say 4x equals 2 plus 5x, right? We don't have to say 2 plus 5x times 1, right? That's redundant. We don't have to do that. It's the same thing. We don't have to say times I, right? So I'll leave it there just so you can see what we actually get, but you won't see this in the actual equations online because it's assumed that this is kind of the same as multiplying by 1. So we have this expression now, K S K transpose is equal to this. And if you look at the last equation that we had for P, the covariance matrix P, before we started taking the derivations on K, what we saw was that P of T, right, or P, I'm not sure if we did with time T, but P was equal to P bar of T minus K C P bar minus P bar C transpose K transpose plus K S K transpose. Right, this was the last equation that we did. And now we see we have a definition for K S K transpose, which is right over here. So if we plug in this definition for K S K transpose into here, right, if we just do a substitution right into here, what we'll see is that here we have negative P bar C transpose K transpose, and here we have plus P bar C transpose K transpose. So these terms will actually cancel out. If we were to actually plug this in, we'll see that they cancel out. So this entire part of the equation, we can kind of just cross it out because it cancels. So what we're left with in the end is P transpose is equal to, I'm sorry, PT, not P transpose, P of T is equal to P bar of T minus KC P bar. And that's it, right? We reduced it a whole bunch. And similar to how in the previous videos we were able to take out certain common expressions, here we're able to do the same. We see a P bar here and a P bar, I guess I'll make it of T, sorry if I didn't put that, but P bar of T, just to keep it uniform. So now we can actually extract an identity matrix, I minus KC times P bar, and this is exactly what we have. Now we have that P of T, or P at time T, is equal to I minus KC P bar of T. And this is now the update step. Now we can actually think of this as P hat of T, right? P hat of T is equal to I minus KC times p bar of t. Right, but you're thinking, where did I get this p bar from? Right, we were never talking about a p bar. But in the first video, in one of the first videos, I mentioned there was a prediction step for this covariance matrix P. It's just I didn't explain it until now. And now's the time to actually explain the prediction step. So the prediction step for this covariance matrix is very similar to the one that we did for X. What we have is that P bar of T is going to be equal to A times P hat T minus 1, right? So the previous one, you know, the one that the last update that we did for P times A transpose plus some noise, and I'll just say plus noise for now, but this noise is actually captured in another covariance matrix, which usually goes by Q. We haven't already used Q. Yeah, it usually goes by the term Q, which is just the covariance of the noise that we get when we're actually doing these updates for the covariance matrix. But this is exactly what we have. This is the update. So why is it more natural to talk about it now? Well, this is following the same property we talked about a little bit earlier with the covariance matrix. We're assuming that P bar of T, the way that we were estimating, is just a covariance of two other variables. And in this case, those two other variables just happen to be multiplied by this factor A, which is what we used in predicting the state X. We said x bar of T was equal to A times X hat of T minus 1, and then we kept going on with that. But this is the same exact variable A, the same matrix A that we used for the prediction on X, and now we're just using it here. So what we see is that we're using the same covariance matrix rules that we talked about a couple of videos ago. We see that this P is just going to be a covariance on something else, so we're just extracting the A and saying that it's A times the covariance of B times A transpose. But we looked at the covariance of B was just a P for something else. So it might turn out to be something like A times the covariance of maybe X of T minus 1 minus X bar T minus 1, or X hat of T minus 1. Right, and we see that the covariance of X T minus 1 minus X hat of T minus 1, this is just the last updated P matrix for the time step T minus 1, so we can perform that substitution. So I hope this actually clears up the rest of the definitions of the Kalman filter algorithm and why they all make sense. So you see the linear algebra equations, at the end, all we're trying to get to is this. This is the ultimate step of the Kalman filter algorithm, is to be able to figure out what K is, and they make it, you know, meaningful variable. Well, not really that meaningful, but they say S of K or whatever, you know, we use this variable S instead of having to type out everything every single time. But the ultimate goal of the Kalman filter is to get this Kalman matrix K so that we're able to perform the update on X, and so that we're also able to perform the update on P right over here. And again, that's just the ultimate goal of the Kalman filter. You update your state and you update your covariance matrix. So at the end, hopefully your covariance matrix, you're minimizing the trace so that you're actually very confident as to where you are. So before this video ends, I think I have one more minute to talk about this. I want to talk about some of the limitations of the Kalman filter we just described. There are a couple more Kalman filter algorithms, most notably the extended Kalman filter. But this Kalman filter, I think in one of the earlier videos I mentioned it's not very good for non-linear states. And what I meant is that if your acceleration mu is either 0 or some constant greater than 0, this is fine. Because what this implies in the first case is that your acceleration is like this, right? This would be your acceleration. And so this would imply that your velocity is linear. Okay, pretend that went through the origin. And your position, you know, if your acceleration was 0, your position would be linear and your velocity would be constant, but then this means that your position is quadratic. And it turns out that this Kalman filter actually does not too bad of a job estimating quadratic state spaces and quadratic positions. But once you go into something like cubic or anything else that's a little more interesting, the normal Kalman filter we just described here fails. So we would actually need to take a look at a different type of Kalman filter algorithm known as the extended Kalman filter, which actually does pretty well on non-linear states. But anyways, most of your applications could possibly be solved by this normal Kalman filter with the linear model. So I hope this video or series of videos has helped you better understand the Kalman filter, and if there's anything I can do to improve my videos or this explanation or something you didn't get, please feel free to ask me. Thank you for watching.